Hey, thanks for coming, and thank you for the opportunity to present my work. It is joined with Jacob Mathern, Carola Mezaros, and Avery Saint-Dizier. So Jacob was a member here last year, and I was with him telling him very enthusiastically about the objects that I were working at that time, the class of Lorentzian polynomials. I'll tell you about those guys later. And I was very excited about those at that time, and I was even telling Jacob that everything that you have seen in algebraic combinatorics so far, every polynomial, must be Lorentzian. And right next to us was Carola Mezaros, who was also a member here last year, who was talking to her student, Avery Saint-Dizier, about some other polynomial in algebraic combinatorics, which is, of course, Schur polynomials. So, of course, the conversation flew into the topic of whether Schur polynomials are Lorentzian. And Avery quickly came up with a counterexample to that, and that's the beginning of the story. So let me start from the very beginning and tell you a little bit about Schur polynomials. These look like this. There's like S, and there's subscript lambda, and it has certain number of variables. Let's say it has n of them. And it is a very ancient object. That goes back well beyond Schur. So here, lambda is a partition. And by that, I simply mean a sequence of weakly decreasing non-negative integers. Let's say I have n of them, same as the number of variables, where I'll allow some of the parts of the partition to be 0. And let's say it is a partition of, say, the number d, which is sum of all the lambda i's. And then this will be a homogeneous polynomial in the variables x that has degree d. The first one who thought about these polynomials was Cauchy. And according to him, by definition, the Schur polynomial is a ratio of determinants. So it's the determinant of the n by n matrix, whose entries are x of a j of n minus I plus lambda I, the ith part in your partition, divided by another determinant, which is xj of n minus I. So van der Molen kind thing. So he noticed that this expression is actually a polynomial. And furthermore, it is actually a symmetric polynomial. It is symmetric in the variables xi. And not only that, when lambda varies over all possible partitions of given number d, these symmetric polynomials form a linear basis of the vector space of degree d symmetric polynomials in the xi's. Okay. And some people followed this work. I mean, once you have one of the many definitions that I'll give you right now, you can start playing many of the games, because these are the one of the most fundamental bases of the space of symmetric polynomials. So once you know that they are bases, you can start asking questions like, what happens if you multiply two of them and expand in the given basis? And ask about the structure constants and etc. And a few years later, Jacobi came up with equivalent definition, which is obviously a polynomial, which is also a determinant. So this time it's the determinant of n by n matrix, whose entries are h of j minus I plus lambda I in n variables, where this time h is the complete symmetric polynomial in n variables of indicated degree. So from this point of view, Schur polynomial is clearly a symmetric polynomial, and is a polynomial, of course. The sum of all monomials in these variables of given degree. And later, Kostka approached these polynomials as a generating function. So to him, this polynomial is a generating function. So it's a sum of k of lambda of a mu and the monomial corresponding to mu. Okay? So let's say you take this or that expression and write it down as a polynomial, and you'll get some numbers. And the question is, what are those numbers? So this k lambda mu is what we now call Kostka number. Associated to a partition lambda and another integer vector, say a composition of the same number mu. And it is the count of these combinatorial objects called Young tableau. Of shape lambda and weight mu, sometimes also called semi-standard Young tableau. So let me explain very briefly what Young tableau are by a simple example. So let's say I have a partition of 3, which is 2, 1, 0. In this game, you view a partition as a collection of boxes. Like this. So you have 2 boxes in the first row, 1 box in the second row, and 0 box in the last row. And Young tableau is a filling of the boxes with numbers from 1 to n. But you don't want to put numbers in an arbitrary way, but under the rule that says that the sequence you get by reading the numbers along every row is weakly increasing. And also, the sequence you get by reading the numbers from top to bottom along every vertical column is strictly increasing. So if you want to fill in the boxes with 3 numbers, say 1 to 3, then all possible ways of doing it will give you the Schur polynomial in 3 variables, as lambda, x1, x2, x3. And the result will look like this. So I'll have monomials like x1 square, x2. And I know that the coefficient here is 1 because there is only one way I can put 2 1s and 1 2 here. I'm forced to do 1, 2, 1. And similarly, I have x1 square, x3. And I'll have x1 x2 square and 2 times x1, x2, x3 and x1, x3 square and x2 square, x3 and x2, x3 square. And that's it. So all the numbers are 1 except for the 2 here, because there are 2 different ways of filling in the boxes using all 3 numbers. So I can do this or that. And both of these obey the 2 rules. Okay. Okay, and then Schur comes in and revealed something truly interesting about these polynomials. I don't clearly understand the initial fascination about these polynomials. I mean, you can, once you define it, you can play interesting games like forever, because they obey many of the highly non-trivial combinatorial identities. At this point, Schur realized that would be also of big interest to like modern day mathematicians. So he noticed that this homogeneous polynomial is actually the character of the irreducible representation say v lambda of our favorite group G, L, and C. So here v lambda is what we now call the highest weight irreducible representation corresponding to lambda. And we also call it the Schur module. And these are all the polynomial irreducible representations of this group. So. And the enumeration of Kostka obtain a new meaning when viewed from this perspective. So Schur module, well, it's a module over GLN, but it splits further into module over the torus inside the general linear group. Called weight spaces. Let's write it like that. And this is the weight space decomposition of V lambda, where each V lambda sub mu is an eigenspace for the torus section, where eigenvalues are attached to mu, or x to the mu. And the dimension of these weight spaces, v lambda to the mu, is the Koska number k of lambda mu, which we may now call weight multiplicities. Of v lambda. So now whenever we see a picture like this, we are having in mind some sort of a irreducible representation of the general linear group. And for each monomial, I have a weight space. And the coefficients that we now see, 1s and 2s, those are dimensions of the weight spaces. Okay. And many, many, many things happened since. So the unifying theme is the relation between representation theory and this symmetric function theory. And maybe soon after or around that same time, it was also noticed that these polynomials are governed by certain geometry, or precisely what's called the Schur calculus, because these polynomials represent cohomology classes of Schubert cells inside the cohomology of a Grassmannian. Okay, so I'll skip most of the interesting things that happened since then, but focus on one particular aspect of this polynomial, S lambda. So we call it convexity properties. And it was noticed from very early on that there is something very convex about S lambda, although it was not so easy to precisely formulate what we mean by that. So first of all, let's think about the Newton polytope. So Newton polytope, what is it? It is the convex hull of the exponents of all the monomials that appear in the expression for S lambda. And people knew that this is a very, very special type of polytope. So what I do is I take the convex hull of the support of S lambda, by which I mean simply the set of all monomials that appear with non-zero coefficient in S lambda. And this is what we now call a generalized permutohedron. Which is by definition a lattice polytope, all of whose edge directions are of the form EI minus EJ. So a root in type A. So all the edges point very special set of directions. And in this case, it's even a special kind of generalized permutohedron, which is simply the convex hull of an orbit, the SN orbit of lambda. So you permute the entries in lambda so that it becomes non-partitions in all possible ways, and then you take the convex hull. Okay, but what is clear from the representation theoretic picture, but maybe not so in the combinatorial meaning interpretation, is that the set of monomials, the support of S lambda, has no hole in it. In its convex hull. So you have this generalized permutohedron, and you start from a lattice point. And you apply this operation. You walk one step by EI minus EJ in any direction. And you will see the non-zero coefficients all along until you completely leave your permutohedron. So the support of Schur polynomial is a set of all lattice points inside its convex hull if you use the right lattice. So that's one convexity, although very weak form of it. And people knew it from ancient times. But sometime in the 80s or even 70s, I'm not too sure, people realized that this Newton polytope is the image of a symplectic variety. So it's actually the moment map image of another orbit of lambda under some other group. So of the co-adjoint orbit of lambda. And maybe this was one of the motivating examples for people who lived in that era to develop some sort of a convexity properties of moment maps. So at least in this case, it was clear from early on that the moment map images of certain symplectic varieties are actually polytopes. And in this case, a very special type of polytope. So there is no need for us to go into details of this picture. But one thing that I want to point out from this is that once you view the Newton polytope of S lambda as the moment map image of a symplectic variety, you see that it's not just a polytope. It's equipped with a natural measure, the one that's pushed forward from the symplectic variety. There's a measure on the symplectic variety, the Liouville measure, and you can push forward this measure, and you get some natural measure on the Newton polytope of the Schur polynomial for any partition. So in other words, this Newton polytope is the support.
Is there a singular symplectic variety mapping to it? Is the symplectic variety mapping to it uniquely determined?
No, I'm having a specific one, the orbit of lambda. Okay. On the compact group corresponding to GLN, let's say SUN. So I'm saying that our permutohedron is the support of what we call the Duist-Math Hackman measure, which you can write it as a multiple of the usual Lebesgue measure on our polytope. So let's say f of dh corresponding to lambda. So it's some function of mu, and there's a Lebesgue measure in the mu coordinate. And this is a remarkable function. So it's turns out that this is a continuous piecewise polynomial functions. And the chambers inside the permutohedron on which the f of a dh is a single polynomial is also determined by the combinatorics of lambda and so on. You can go on and on. But from our point of view, what is most interesting is that this measure is actually a limiting measure for weight multiplicities. So in the following sense. So it turns out that, and this is essentially Hackman's theorem, that the push-forward measure is a limit, say as, let's say L, as L goes to infinity of k of a lambda mu, where I replace lambda by L times lambda, where L is approaching infinity. And I put it with a Dirac delta measure placed at mu divided by L. And I normalize the whole thing so that it has union mass. So it's the sum over mu, and I divide by this number, sum over mu of k L lambda comma mu. Okay. So this is a discrete measure. So I put point measures by looking at the representations that I obtain by all the large multiples of the given representation lambda. And then it will have certain distribution of weight multiplicities inside the permutohedron. I look at dilations and dilation, and then I scale back. So in this limiting process, I'll get the denser and denser set of lattice points, each decorated with weight multiplicities of limiting representations. And the limit of this measure turns out to be this continuous measure. That interpretation is interesting because soon after, Graham and also Andrei Okounkov have noticed that in such a situation, and maybe also in a slightly more general setting, that the log of this Dirichlet-Hackman function associated to a partition is not any function. It's in fact a concave function. So the geometry of the co-adjoint orbit tries to tell us something about the distribution of weight multiplicities of a representation of the general linear group. And in this sense, in this setting, people usually say that the weight multiplicities are asymptotically log-concave. So if your L is very, very large or something. And people in this area express this fact by saying that weight multiplicities so log-concave for fixed lambda in the classical limit. And in 2000, Log-concavity wrote an influential article titled "Why Would Multiplicities Be log-concave?" So the answers to why would questions are always interesting, especially if they are not proofs. Okay. So he wrote something about it and took a physical analogy to explain why would multiplicities be log-concave. Even before taking the classical limit.
What kind of physics?
Well, some sort of entropy was there and statistical physics, and entropy is a concave function. Okay. But I'm not sure how to go from that to irreducible representations of GLM. But okay, but there are statements that naive mathematicians can understand, and one of them was this conjecture that the Littlewood Richardson coefficients, let me write it like C of a nu of a kappa of lambda, is log concave in nu and kappa and lambda. And all three of these objects are partitions. So this C is a discrete function. So what he means by this is if you take the log of these integers, and then you get a function defined on some lattice, say the lattice of triples of partitions. And if you take any line on that cone of partitions, and if you read off any sequence along any line, then the numbers you see, actually this AI should be C, must always satisfy this. So this Littlewood-Richardson coefficients are the structure constants for the multiplication of the Schur polynomials, and express it again as a linear. But ignore that if you are not already familiar with them. But for us, let me just remark that the Littlewood-Richardson coefficient contains, as a special case, the Koska coefficients, the weight multiplicities that we were interested in. So the actual rule goes like something like this. If you have a k lambda of, say, mu, let's say it's a 4, 2, 1. And then this is C of, I need triple of partitions, so that the largest partition that I put here has 4, 2, 1. So I don't have any overlapping boxes in the vertical side, and I just fill this in. And here I put this dotted boxes back again, and I keep lambda. So there is a linear transformation so that the restriction of C to a subspace is K. So this conjecture is actually stronger than the corresponding statement on log-concavity of weight multiplicities in our previous sense. But there are different aspects to this conjecture. So it's a very strong statement that implies a few things that people were very interested in at that time, like
Could you repeat the
the relation between k and c. So lambda is fixed. Let's say I have some mu, which is, let's say, 4, 2, 1. I slide the boxes horizontally so that I have no overlapping boxes in every column. And I do that in most efficient way. So this is a skew shape. And here I put a new collection of boxes that were missing, so it's not in here. I keep lambda. So if we want, we can write down a formula, a linear expression. This is just a
Notation-wise, wasn't the lambda the distribution of boxes and the mu values you put in it?
yeah. Lambda also somewhat looks. Lambda is partition. Mu is not necessarily a partition, but it can be. But this is an illustration. Okay. So this is what people knew. Weight multiplicity log concave in the classical limit. So to go from here to there, Okunko made 3 jumps. So he replaced k to c. And not only that, mu to this triple. Right? So here, the log concavity of the function that you're interested in has mu as a variable. And lambda is fixed. And you vary mu. Here, he is moving all the parameters. And most importantly, he moved away from the so-called classical limit. So I'm not entirely sure what's the opposite of classical limit. So let me just say, before taking limit. Hmm?
Is it easy to see that the classical limit of the conjecture is valid?
I think that is his statement.
No, what do you mean, like the little the triple multiplicity?
That's not clear. But I think Okunko showed that in classical limit in his paper as a further evidence of by similar technique, as I understand. And people worked on it. And Chindris, Dirksen, and Georgi Wayman in 2007 found a counterexample. Although several of the interesting implications of this conjecture, like the one that's needed to settle what is called the Horn's problem on eigenvalues of Hermitian matrices, and Fulton's conjecture on the saturation of Littlewood-Richardson cone, or some things like that, that are all turned out to be true. But the conjecture itself failed. And the largest partition that's involved in the smallest counterexample is it's not so large, 504 or larger. So it's either small or large, depending. It's right in the middle. So we have nothing to say about C right now. So I'll talk about just the weight multiplicities of irreducible representations, but before taking the limit. And only, of course, in mu variable, but there is a catch. Here's one of our results. And this is a discrete version of the main theorem. That for any partition mu, let's say lambda, and any mu, k lambda mu square is at least this large. K lambda of mu plus Ej minus Ei for any I and j in n. So the weight multiplicities are log concave along root directions. You start with a reducible representation. You start at some point, one of the weights, and you walk along any one of the chosen root direction, Ei minus Ej. And you will encounter a certain sequence of numbers, and those numbers are always log concave. So it's slightly stronger than the version for k, mu, and prelimit because I'm only walking in special directions, the root direction, and I'm not testing convexity along arbitrary direction. So my feeling is that a convexity may actually fail in arbitrary direction, but we do not have a counterexample to that.
Sorry, could you check the indices on the right-hand side? Minus Ei plus Ej.
And Ej minus, okay, that's right. Eij, okay. Thank you. Right. I need 3 of them. Yeah. And there is also a continuous version of the main theorem. Which describes an analytic property of the Schur polynomial. So for this, I need a linear operator. Operator n, where n stands for the normalization, by saying that it acts on monomials by dividing the factorial of the exponent. So this normalization operator from the generating polynomial point of view turns the usual generating polynomial into exponential generating polynomial. A very simple linear operator. And the result is that for any partition lambda, if you take the log of the normalized Schur polynomial, viewed as a function on the positive orthant, it is concave, continuous function, when S lambda is not identically 0. And the main theorem is n of S lambda is a Lorentzian polynomial. And the result is not true, whatever Lorentzian means, if I do not take this normalization n. So let me briefly tell you what this Lorentzian property is. So this Lorentzian property implies both the discrete and continuous version of the concavity statement. And I introduced this with my work with Patton and Stockholm. And a polynomial f with non-negative coefficients is Lorentzian if you have two conditions. The first is that the support of F, the set of monomials viewed as a subset of the lattice, satisfies the so-called exchange property. The same exchange property that you see in matroid theory or linear algebra of basis. And the condition turns out to be equivalent to maybe a more familiar condition, which can be expressed by saying that the convex rule of the support, or the Newton polytope, is a generalized permutohedron. So all the edge directions are EI minus EJ, and the support has no holes in it. It is the set of all lattice points inside the generalized permutohedron. So that condition is equivalent to the matroid exchange property, or the polymatroid exchange property. And in addition to that combinatorial condition, you need a spectral condition, which says that all quadratic polynomials of the form partial alpha of f, where alpha is a lattice point, and this is a differential, monomial differential operator corresponding to alpha, have at most one positive eigenvalue. Okay, I know it doesn't look like it, but I think it's a really cool definition. But very unfortunately, I don't have time to justify why I feel that way. But let me just remark that these properties implies the discrete and continuous versions of the statement. Say, for any polynomial, there's an analogous statement, and Lorentzian property implies it. And let me just convince you at least that this Lorentzian property, 1 and 2, is very easy to check. Say, compared to one of its consequences like this. Okay, so things like this is a statement that's hard to make precise. So it depends on who you are, and it depends on what you're comparing it to. But think of this. Let's say I give you a degree 37 polynomial in 52 variables. And I ask you whether, if you take the log of that polynomial, is it concave on, say, positive orthant? That would be very hard to check. At least I have no idea how to start typing into computer. I mean, according to definition almost, what you can do at least is you form this gigantic Hessian matrix of log of a polynomial, many things, and you hope that you can say that the principal minors have fixed sign on all of positive orthant, and I have no idea how to do that. But if you look at these two properties, that's entirely combinatorial. You form the Newton polytope, look at the edge directions. Are they in the root directions? Yes. And then you proceed to 2. And you look at all the partial derivatives. These are just a bunch of square matrices whose entries are the coefficients. And we are pretty good at computing eigenvalues or taking the signs of them. So there will be maybe 500 of them. We can do it. So at least if you have a member in your team who can talk to computers in real time, then at least the conjectures are very easy to check in many, many cases. And Avery is graduating this year, and he has this supernatural ability of communicating with computers, so your department may want to hire him. Okay. And also, what I'm trying to sell these days is that these properties are also easy to check by humans. So they should be useful in proving things. I mean, this is our favorite paradox in mathematics. Somebody asks you to prove a statement like this. Oh, you have no idea. How do you prove it? But we have our favorite tool. I mean, oftentimes, in almost all cases where we can hope progress, a harder property is easier to prove. So that's usually impossibly hopeless. But this is oftentimes miraculously sometimes easier to prove. But unfortunately, that was not the case for our project so far. So how do we prove our main theorem that fortunately or unfortunately relies again on the Hodge theory? So what we do is we rely on the Hodge theory of a projective variety. And the variety in question is constructed as a degeneracy locus of a certain vector bundle homomorphism that we construct somewhat in the style of Fulton. And we do some intersection theory computations. And the Hodge theory on that degeneracy locus implies the Lorentzian property. The variety is singular, but maybe I don't care. I don't even care. Okay, so I have some time left, and I'll give you a bunch of conjectures. So I'm willing to say that everything natural you see in algebraic combinatorics is Lorentzian, if you normalize it in the right way. So
Can you say a word, Lorentzian versus, say, stable or hyperbolic?
So Lorentzian is exactly stable for quadratics. Let's say you want to construct a theory that is equal to stability for quadratics for this spectrum condition, and your class is closed on the partial derivatives. Then the largest family you get is this. And this combinatorial condition is forced on you.
Can't see this from the more familiar ways of showing things are stable, like Li Yang and things like that.
So probably this, in general, the normalized Schur polynomial does not belong to any more restrictive class that's defined so far. So these most of them live at the very boundary of the space of Lorentzian polynomials. Oh. Okay. Okay, first, so we mindlessly tried all the polynomials that generalize Schur polynomials that we know of. So first of all, there is this Schubert polynomial. That controls the cohomology of flag varieties in the same way Schur polynomial controls the cohomology of Grassmannians. And combinatorial is recursively defined by divided difference operators. And the conjecture is that if you normalize it, then it's Lorentzian. And we tested this for all permutations in Sn for n up to 8. And there are these Schur polynomials. And these are the same Schur polynomials where you allow skew shapes. And you look at the generating function, or rather you look at the exponential generating function, and we conjecture that is Lorentzian. So we check this with at most 12 boxes and 6 rows. And there are these Schur p polynomials introduced by Schur and extensively studied by MacDonald in relation to Hall polynomials and representation theory, etc. And we conjecture that this is a Lorentzian polynomial. And we tested the conjecture with similar range. And there is this Grothendieck polynomial. Normalized. Let's say G of W, which controls the K-theory of flag varieties in the same way Schubert polynomial controls the cohomology. So this is not a homogeneous polynomial. So what I'm going to do is take homogeneous component in degree k, and then it will be alternating in sign. So I put -1 to the k here. And the conjecture is that each of the normalized homogeneous pieces are Lorentzian. This is checked for all permutation with 7 letters. GW is a Grothendieck polynomial. It's defined by the inhomogeneous recursive divided difference relation that looks nearly identical to the one that defines. So it computes the K-theory class of Schubert varieties inside G mod B. And there are these little key polynomials introduced by de Mazur and in combinatorial context studied by Lascaux and Schützenberger. And we conjecture that if you normalize them, they are all Lorentzian. And we also check this with mu at most 12 boxes. And so that is the big mystery. So I can tell you my intuition. So if you know some of the stories behind this, you know that they have a geometric origin. And most of the cases, they describe some sort of cohomology classes. And this is the usual generating function for something, and it usually describes cohomology classes. And in order to get the Lorentzian property via Hodge theory, you need some sort of dual statement. And my feeling is that, well, this sounds like nonsense, but these guys are homological. These guys are cohomological. So maybe I should have written by the differential operator associated to mu, so that these are actually the dual bases to each other. And to me, what this numerical conjecture seems to suggest is that there is some natural construction of geometric varieties, which is not the usual one that's known at present, like Schubert varieties and so on, which explains these concavity properties. And let me just end the talk by lastly introducing my favorite conjecture, which is this. We conjecture that the same property holds for any lambda in the integral weight lattice of SLN. So for you take any weight, and there is a highest weight simple module with that highest weight. It has finite dimensional weight pieces. You look at the weight multiplicities. We conjecture that they are always log concave in any of the root directions.